Hi, I'd like to talk with you about the formulas for left and right sums, for Riemann sums. This is in the world of the building blocks for definite integration. And I'm going to do this video without summation notation, and then we can work on summation notation for this at another time. Okay, so our goal is to approximate the area underneath this curve between A and B. So between there and there. So I'm only interested in this area right here. And because computing things with curves is hard, we're like, okay, fine. I'll work with something easy. I know how to deal with rectangles. No problem whatsoever. So we're going to be approximating via rectangles. And I want to talk about the sum, or the formula for this area in terms of actual values coming from this plot right here. So the first thing that I want to do with you is name things. That's one of the most powerful actions that we can take as mathematicians, is to name things and name them well. And even a poor name for something is usually better than no name at all. So I'm going to start and label A to be x0, x0, the left one. And then I'm going to call this one x1, x2, x3, and so on until I get to x n minus 1, and finally x sub n. And I read that as x sub n when I verbalize it. And that's where my interval of interest stops. So I'm between x0 and x sub n. The next thing I want you to notice is that the functions, the height of the function is determined by the x value, and that I can label those pretty easily. That this height right here is f at x0. This height here is f at x1. This height here is f at x2, and so on until this height right here is f at x sub n, and this one right here is f at x sub n minus 1. Okay, so I have x positions determined on the x-axis, and then I have heights determined by my function. So let's explore using the left endpoint of each interval to compute an estimate for the area underneath the curve. So for every interval here, I've set them to be uniformly spaced, which is good for us as humans when we're learning. It's bad for computers when they would do this numerically. So we'll take the left endpoint, and I'm just going to sketch in what those heights would be if I were to take left endpoints. I know these are a bit wider over here. Just ignore my manual. Oh, I don't need that one. That was outside of my interval of interest. Oh, and that was kind of one of the points I wanted to make when doing the left endpoint one. That mistake I made right there factored in nicely to what I wanted to show you, which is that I'm only ever going to use n of these x values, but there are n plus 1 of them, because like here from 1 to n, there are n of them, and then there's 1 extra, or from 0 to n minus 1, there are n of them, and then there's 1 extra. All right, so when doing the left ones, I don't use the rightmost endpoint to determine the height of a function, because that would only ever be used if I was doing the right endpoint to determine the height of my rectangles. Okay, so the heights are given by my function values, and the widths are not given by x's, but are given by the partition width. And so the difference here between consecutive, excuse me, between consecutive values right here is what we call delta x. Okay, and we're assuming all of those to be the same because we're doing a uniform partition. So I have a uniform partition, which means that I have one delta x value for all of these rectangles, and I can compute that by taking the total width of this interval, which is b minus a, right? That's how far I have to go to get here. And then how many pieces have I divided it into? I've divided this into n pieces. Okay. So delta x is b minus a over n. That's the width right here. I can use these two symbols interchangeably. And when I first start writing this, I'm just going to leave it in terms of delta x because it's fewer symbols. Delta x is one symbol. Okay. So when I write down the left sum, I have the height, which is f at x naught times the width, which is delta x, plus f at x1, that's the height of the second rectangle, times delta x, plus f at x2, that's the height of the third rectangle, times delta x, plus, and so on, plus the very last one is determined by f at x sub n minus 1, and then the width is still the same as delta x. So I have n total terms right here. I better not have n plus 1 total terms. I have n total terms going from 0 to n minus 1. A common error when doing these kinds of calculations is to accidentally include one more. And so remember, we're always going to drop either the left or the right when we do this process. Now, each of these terms has a delta x in it. And so what I'd really like to do is factor them out. And let's rewrite it down here. L sub n is equal to delta x times the sum f of x naught plus f at x1 plus dot 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 plus f at x sub n minus 1. And I close it. So that's the formula for the left sum. Because all of them have the same width for the rectangle, I get to just factor it out, and all I have to do is sum up the function values and then multiply by delta x on the outside. Let's determine the formula for the right sum, and then I think we'll probably call it good. I might make one concluding note at the end. Clarification. Okay, so that calculation that we just did was summing with the left endpoints. So now let's repeat it and sum on the right endpoints. Okay, so I'm going to erase my heights from my diagram because I'm going to determine them by the right endpoint of the interval this time instead of the left. So it's determined by the right endpoint, which means it's determined by like that. And there's no point to the right of this because this is the end of my interval of interest. Okay, so let's write down what R sub n is equal to. I'm going to start at the left, but they're determined by the right endpoints. I've got, well, the height of this one here, we can see it in the label right here, is f at x1. And the width of the rectangle is still delta x. The height of the second rectangle is f at x2. The width is delta x. Until I get to the last one, which is going to be determined by x sub n times delta x. And just like last time, because we have a uniform partition, this is one of the reasons we use a uniform partition when we teach this. I get to factor out the delta x from all of these, and I get to write that R sub n is equal to delta x times f at x sub 1 plus f at x sub 2 plus f at x sub n. Okay. So these two sums are different in very minor ways. Let's compare the two formulas for the right endpoint method and the left endpoint method. And then I'll tell you why we subscript them. Okay, So they both have f of x sub 1. They both have f of x sub 2. They both have f of x sub 3. This one here has f of x sub n, but is missing f of x naught, right? What's not present? There's no f of x naught in this one. And yes, this one has f of x sub n in it. That's because I started my sum, I did my sum on right endpoints, and x sub naught didn't come into account. X sub naught isn't the right endpoint of any rectangle, so it's missing. But I pick up that one, as opposed to this one, the left, I have x sub naught, but no x sub n term in it, because that was on the right side, and it's not the left endpoint of any rectangle in my partition. So that's like something that you should pay attention to when doing this. And the only other thing I wanted to say is why do I have R sub n and L sub n? Well, you're given a number of rectangles, you generate different sums. So like the value you get when you use like 3 rectangles is going to be different than the values when you get when you use 5 rectangles, which is different from the value you get when you would do like 10 or 20 or 100 or 300 or any number but infinity, any positive number. So those are the formulas for the right and left sums of for approximating the area underneath a curve. And I omitted the summation notation, and we'll do that in a different video. Thank you so much, and happy integration.